All right, let's get started.
Does anybody have any idea what you can see on the picture behind me? Wave your hand or shout if you know it. Okay, shout louder because I'm not hearing you yet. Control room, yes. What were you saying? Police, yeah, sure. Any other ideas? This is the emergency room of the Dutch police in The Hague. So whenever you call the emergency number, it's 112 in the Netherlands. Here are the fire brigade, the police, and the ambulance to help you with your emergency call. So this room is one of the locations that my teams at the police are building software for. So my name is Bert Schrijver. I work at Open Value, which is a small Java startup in the Netherlands. But since the startup world is so hard, I need to work 2 jobs. So we also work at JPoint, which is a Java consultancy shop. My current assignment is at the Dutch police. And I also run the NLJUG, the Dutch Java User Group. So do you have any members from the NLJUG in the room? All right, 1. Thanks for the support, Brian. So for the next 50 minutes or so, I'm going to I'm going to start with a short introduction about what I'm going to talk about, set the stage, talk about how we handle methodology, how we handle culture, what type of methodology we use, the architecture that we've built stuff on, and the platform we use, how we build and test our front end. Obviously, we have a backend too, how we develop and test stuff, how we build stuff, how we deploy, and how we run and monitor it in production. And I'll end with the challenges we've had and by looking ahead on stuff we'd still like to work on. So a short disclaimer first. I'm not presenting a best practices talk. I'm just sharing how we work and what works for us. It might work for you too. It might not. It always depends. I'm going to share a lot of stuff from different angles. I will not really go in depth because I don't have time to do so, but you're free to ask me afterwards to reach out on Twitter. So I'm going to share everything about how we work and the technology that my team uses. I'm going to tell nothing about the type of system we use and what they're used for, but obviously you're always free to use your imagination. So the Dutch police is a fairly large organization, about 65,000 people, of which about 1,500 work in IT. So how many of you have been to the Netherlands before? Okay, well, which cities did you visit? Okay, shout please. Did anybody go to Amsterdam? Okay, so I won't be asking you questions about what you did in Amsterdam. It's a nice city, yeah, there's lots of stuff to find out there. Is any of you familiar with the Dutch police? There's one guy up front here. Okay, I won't ask you anything about that too. So I work at the product line Cloud, Big Data, Internet, where a couple of teams are building fairly high-tech stuff in a private cloud we're building ourselves. And we are building applications that support various police-related teams. So that's about what I'm going to share. And we do everything ourselves, so development, maintenance, support. And what I'm going to share is about how our department works. It's not how the entire police works. We're about 30 people. So let's start by diving into a bit of methodology. So as I said, we have 5 teams, and those teams have separate backlogs. So what I always like is one team, one product owner, one backlog, because then you'll never have any arguments about what to work on. Our sprints are synchronized, so whenever we start a new sprint, we have an overall planning with the teams to see if there are any dependencies between the teams. And our planning ritual is fairly minimal. So this might offend you if you're kind of a Scrum purist, but we don't really use story points to estimate stories and to measure velocity. We only use story points as a way of determining how many work will fit in a sprint. So what we do when we do planning poker, when we estimate our stories, we say that one story point equals 1 man day of work. And since the teams are fairly comparable in terms of productivity, this works for us. So then we estimate stories to either 1 or 2 or 3 or 5 days of work. Whenever we start planning for a sprint, we ask around the team, like how many days will you be available for this sprint? We add this up to a number, and then we start filling the sprint with stories until we reach this number. And this works fairly well, but we only use it as a tool to predict how much work will fit in the sprint. and we try to measure productivity in other terms. For example, how happy our customers or our users are. We try to make usability tests part of our sprints. So we ask people from the field, and in our case, I think it's a bit easier than when you're making a public product, because we know who our end users are. They must be any of those 65,000 people in the police organization. So we can just ask them, some key users, please come in and take a look at the new version of the system we've built and tell us what you think of it. Use it and see if it works for you. So we try to make those usability tests parts of our sprints. We try to minimize the amount of meetings we have. So obviously we have the Scrum cycles with planning and retro and demo and refinements to refine use stories. But other than that, almost no meetings. Since we've grown from one team to 5, we did saw the necessity to build some cross-team structures. So we've set up a couple of guilds, for example, the Frontend Development Guild, the Security Guild, the Performance Guild, where people from different teams have regular meetings, like one every 2 weeks, to discuss like cross-cutting concerns that go over all teams. For example, something like security is something that you can easily forget in your own sprint. So when there's a different group of people that will have a specific focus on security, you make sure that you'll spend time on this at the right time. We use Fabricator to do our project administration. So I'm curious, how many of you have heard of Fabricator before? Okay, couple. Fabricator is like you could call an open source clone of the Atlassian suite. Although the last time I said this, somebody tweeted it, and then somebody replied angrily on Twitter, no, that's not true, we had code review first. And I was like, I'm curious who's saying this, and this turned out to be one of the developers of Fabricator. So I cannot call it an open source Atlassian suite clone, but it's comparable. It has a wiki, it has issue tracking, it has tasks, it has code review, and you can do mockups in there. It's a fairly complete open source suite. It's used by, I think it was created at Facebook. It's used by Facebook, by Dropbox, by Pinterest. So if you're looking for an open source solution to do your product administration in, I can recommend it. So let's talk about culture. We like the values of continuous delivery and DevOps. So continuous delivery meaning we try to build and test our software in such a way that it's always in a releasable state. And DevOps meaning that we have development engineers, operations engineers, and other IT professionals being responsible together for the entire life cycle of our products. We try to focus on keeping feedback loops as short as possible. So whenever we do something, we want to hear something back as quickly as possible. So either automate it, when we push something and a build starts running and tests start running, or not automated, but for my users. So we try to keep these loops as short as possible while actively involving our users in giving feedback and obviously releasing in short periods to production so we can actively get feedback from our users. And we try to embrace change. So we know that the world is going to be different tomorrow. So we rather make the wrong choice today than make no choice at all. So one quote that I like, I think, is from one of the founders from Nintendo. As he said, I reserve the right to wake up smarter tomorrow. And with that in mind, we believe it's okay if we start building something now, we experiment a little, and then we see that's not going to work. It's all right to throw it away and start something over again, as long as we don't spend too much time. And I think this is vital for our speed as part of a larger organization. We try to minimize and, if possible, cut off all dependencies we have outside our department. Because if we depend on somebody else in the organization to do stuff for us that we need to progress, then we can't control this person. So we can't control the speed at which this happens. So we try to keep as much of the stuff we need to do to get from ID to working software in production, keep it inside our team. And this enables us to move fairly fast within a fairly large organization. We invest in people. We don't buy products. So everything we use is open source and free to use. And we try to hire smart and driven people to help us with these open source tools. And we try to be open and transparent and verifiable. So the police is a public organization, so we are paid by the Dutch people. So we try to be verifiable and transparent in the things we do. So we regularly have people over from, for example, from universities or from public organizations who concern themselves with privacy. And we also share some of the stuff we're building on GitHub. So if you go to github.com/politie, which is Dutch for police, you'll find some of the stuff we've built there. For example, Jenkins pipelines and stuff like that. So we have 5 teams, and these teams are responsible for doing everything from idea to working software in production. We don't have separate management or maintenance teams. How do we handle support and maintenance during our sprints? Because that's something that we also need to work on. So we've made this a role that cycles throughout the team. So everybody in the team is on duty maybe 1 day in a week or 1 day every 2 weeks. And we call this the name of the team of the day. So we have 5 teams, and these teams used to have descriptive names. So one team was more focused on platform, one more on backend, and one more on frontend. But we noticed that didn't really work well, because then if somebody who was working in the frontend team needed something, then they need to walk to the backend team. So now we've made the teams more cross-functional and gave them names that don't have any meaning. So they're all shades of blue. We have the Cobalt team, the Indigo team, the Sapphire team, and a couple of others. So if you are, for example, the Cobalt of the day, it means that you have the support role for the Cobalt team this day. So you handle support calls that come in, you take a look at our monitoring systems, and also try to improve the observability of our systems. So for example, logging. We actively work on improving the logging that our application does. So try to go through the logs in production, all the logging that goes on info level and higher, and see, is this logging useful? If there's a logging statement, is it a problem? If so, do I need to act on it? If not, why am I logging it? If I need to act on it, okay, fix it, and then logging should go away. If it's not clear what I need to do, then I need to improve the logging. So go to my IDE, open a project, improve the logging, push it, and if it's important, move to production right away. So I kind of call this like log gardening. We actively work to keep the logging useful. So on a regular day, some of our applications may serve, I don't know, 1 million records or so, and typically there are only a handful of error logs in those 1 million requests. And this helps keeping the logs useful, because if you have 1 million requests and there are 10 million error messages, nobody's going to look at it. So let's talk about architecture a bit. These are architecture principles, and the good thing with principles that you're allowed to derive from them or make them an end goal. So we're not there yet for all these principles, but we try to work on them. So obviously, when you work at the police, security and encryption is important. So we try to encrypt from end to end, so from the browser of the end user all the way to the final point in our data center. Everything is in version control, which helps in knowing who did what and when, and obviously reverting things. We want to be scalable, so everything needs to scale out. We're the big data department, so we typically handle big data workloads. So that everything needs to be horizontally scalable, and we can't have any single points of failure, because then only one thing can break, and then we're out. I think this is one of the most important things. We can't have any runtime dependencies on external systems that we don't control. For example, if we have a fair amount of mapping functionality in our applications. We can't rely on Google Maps there, because if there's a big problem in the internet in the Netherlands, and I don't know, the police network is being DOSed, and we can't reach Google Maps, then we don't know where the problems are. So we've built our own mapping solution based on vector-based OpenStreetMap data. And I would say that this is actually better than Google Maps, but that's probably because we've built it ourselves. But our systems need to keep running whenever the internet in the Netherlands is in flames and halfway down. So this is important for us that obviously you can use Google Maps in our application if you like it, but if not, there should always be a fallback to something that doesn't depend on something that we don't control. We standardize on naming. This seems a small thing, but it's actually fairly big, because this really helps in finding stuff and automating stuff. So if we know the name of the part of the domain, for example, it's, I don't know, geo information, and we know the type of component that we're looking for, so we have services, connectors, syncs, stuff like that. Let's say it's a service, then we know that the name is service-geo. The Git project is called service-geo. The build is called service-geo. The URL for the dev environment is service-geo.dev.something. So this really helps in terms of finding stuff, but also in automating, because now it's easy to create scripts that only need to fill in a couple of variables. We reserve to choose the right tool for the job, and as a result, we're fairly polyglot now. So we now have software written in Java, in TypeScript, C, Ruby, Groovy, PHP, Scala, JavaScript, Python, Go, Perl, and Kotlin. So is this a good thing? I wouldn't necessarily say so, but we have reasons. For example, most of the stuff is in Java for the backend and Kotlin for the front end. TypeScript for the front end. Then we have some C for some low-level network stuff, Ruby because of Puppet scripts, I think, Groovy because of Jenkins pipelines, PHP because of some legacy application, Scala because of the Gatling DSL, JavaScript, I don't know, Python because of some operations scripts, Go because somebody wanted to learn Go, Perl because of some operation scripts, and Kotlin because, well, come on, Kotlin. But the big batch is Java and TypeScript. So I need to warn you, because we're going to talk about architecture. And you know, these architecture diagrams are typically large, and there are lots of boxes and lines and colors, and maybe even icons if you're lucky. So don't be surprised. Here's an architecture diagram. So let me walk you through this. So it all starts at the bottom. We're running on a private cloud we're building ourselves. So these are machines somewhere in a police data center. And we're using OpenStack as cloud software and Ceph as distributed storage. I'll tell a bit more about that later. So it all starts at the right, where we ingest data sources. This can be content from the web, maybe tweets, Instagram, mapping data, some other online sources, and obviously data from internal systems too. So we store the original data of everything we fetch. So we can also always access the original raw data that we fetched whenever we need to prove something to someone. So these data sources are fetched by applications we call connectors. And the sole goal of a connector is to pull data from some remote source. So this can be a connector to fetch geo information, for example. And a connector typically puts a message on a Kafka topic. So how many of you have experience with Kafka? Okay, about half. So you could see Kafka as a distributed messaging system or queue. It's fairly high performance and scalable. So we use it to decouple reading and writing sites from our system. So, and also to handle stuff like back pressure, where we're pulling in data faster than we can process behind Kafka. So these connectors are pulling in data and putting messages on Kafka topics. Depending on the size of the data, it can either be the full message on a Kafka topic or a pointer to the original data stored on Ceph somewhere. And on the other side, we're using also Spring applications that are built using Kafka streams. So these connect as a consumer to Kafka and then process the data. So we could have put all this in a single application, but because we have Kafka in between, we get a couple of advantages. We can scale independently, so we can have more consumers than we have producers. We can easily restart the consumers here. We won't lose messages because Kafka will queue them for us. And we can even replay. So you can set like a retention period on Kafka. So whenever something breaks, we can replay, for example, the past day of messages to put it again through our pipeline. So the stream jobs, it still says Spark here. We moved away from Spark because we had a lot of trouble keeping the Spark cluster up and running. So now just simple Kafka consumers that we deploy as Spring Boot applications. And these streams jobs, they write to data stores, and these data stores tend to be optimized for the goal wherever we use them for. So they're used by services, and these are typical Spring Boot applications that handle REST requests from end users, read something from the data store, and serve it back to the front end. So Elasticsearch whenever a search is important, Cassandra when maybe writing is important to store user data, MongoDB when it's document-oriented, MySQL because we migrated a legacy application that had a MySQL database and we didn't feel like migrating the database. Then there's a front end, a couple of front ends actually that we've built with Angular. These are being used in the browser and on some mobile devices. So we have an LDAP server where all the user information is in, and we are currently halfway migrating from using Kerberos for authentication. So Kerberos is fairly old school and has some interesting characteristics to putting a key cloak in between. So key cloak is an open source, you could call it IAM provider. And with Keycloak, we can easily connect multiple authentication sources. So either a Kerberos token, or maybe OAuth, or maybe login with username and password. And our security model is delegation. So whenever a user makes a call through a browser to a service, and the service needs to call another service, then this call is done on behalf of the end user. So we forward the credentials of the user. So with every call, even if a user calls a service, which calls another service, which calls another service, it's still as if the service was called directly by the end user. So this makes the security model fairly simple. We always know that a call is done on behalf of the end user. There are no system accounts or God accounts. Makes it fairly simple for us to keep security simple and to trace who's doing what where. So let's talk about platform a bit. So as I said, we are running on OpenStack, which is an open source cloud solution. Ceph for distributed storage. And Ceph is being used, for example, by CERN, where the Hadron Collider is. It's a distributed storage system where you can create like a big storage solution of hundreds or thousands of disks. So whenever a machine boots up, the compute and memory resources go to OpenStack, and the storage resources go to Ceph. And Ceph takes care of replication, so all the data is replicated in 3 places, and rebalancing whenever something fails. So what do we do with this cloud? We provide general cloud services for the police organization. Again, you're free to use your imagination. So we're currently growing towards about 500 servers, a couple of thousand virtual servers, around 24 petabyte of storage, and we're about halfway there, I would say. And we're kind of like playing our own cloud provider, which sounds fun, until you notice that you need, of 30 people, 1 person full-time working on networking. Peerings, firewalls, VPNs, network connections. So it's playing your own cloud provider sounds fun, but in practice it's a lot of work. So if I could choose between building my own cloud or just taking my credit card and going to Amazon or Google or Azure, if I had the choice, I would definitely choose the latter one. And in addition to that, we have a couple of thousand desktops that we manage. And their automation starts whenever something boots. So be it a server or a desktop or a switch, as soon as it boots, we start provisioning it. So that's the only way that we can manage this amount of machines with only a small group of people. So if you have hundreds of physical servers and 14 disks per server, stuff is going to break every now and then. It's not a matter if stuff breaks, but when it breaks. So let me tell you a couple of stories about this. So we've automated lots of health checks on machines. For example, on all those disks, we're monitoring the smart values. And whenever we see smart failures, then so smart is a mechanism that hard drives expose. So whenever we see a smart failure, we can, with some certainty, detect that the disk is broken. Then we automatically create a ticket to the people who work in the data center, so that they start working to replace the disk for us. And because the data is replicated over multiple drives, we can easily replace those drives. So it happens that because it's all automated, we typically don't know that there are people working to replace disk. We have it on a ticket system somewhere, but it's all automated. So it happens that our support phone rings, and somebody in the data center saying, "Yeah, so you called, you made this ticket that we need to replace a disk." And they were like, "All right, yeah, probably we did this. Yeah, so I'm in front of this machine, but I forgot which disk it is. So can you tell me which disk it is?" Okay, do you know the service tag of the machine, which is like a small sticker that's on there? Then we can find the IP address, log into it, and see which disk is broken. So, yeah, it's the second disk. Okay, thanks. So is it the second disk from the top left or the second disk from the bottom right? We don't know. So, yeah, I'm pretty sure it's the second disk from the top left. All right, here we go. Healthy disk disappears. Oh, no, that wasn't the right one. Put it back. Okay, disk back. Second one from top left, yeah, that's the broken one. But as I said, because the data is distributed, whenever we lose a disk, it's usually not a problem. Ceph just starts rebalancing, and then in no time, the data is still distributed in 3 places again. So we once had a failure where we lost a significant portion of the data center, and the Ceph needed to rebalance for a couple of hours, but afterwards it was all good. We didn't have any downtime and no lost data. Another thing is we have this thing in my team where something happens, we try to find suitable music for the occasion. So one of my colleagues was working and he turns on this song. I think it was It's Getting Hot in Here by Nelly. So I look at him like, what's going on? And he has this fake smile on his face. And he picks up the phone, he calls somebody in data center. And he said, yeah, so you did some maintenance on this and that server, right? Yeah, we did. So are you sure that you put all the parts back in? Yeah, I'm pretty sure. Did you also put back in these small fans that are in front of the strip you put over the machine? I think I'm going to have to call you back. So what we did is we noticed that the temperature of this machine was going up. So we had some alerts going off, and it turned out that somebody forgot to put some fans back in. But you know, as long as you're working on having your data replicated and clustered, then you're typically good in this situation. So how do we manage this? Hundreds of servers, thousands of desktops, and thousands of virtual servers. Obviously by automating it. So we're big fans of seeing our infrastructure as code. So we use Terraform to connect to the OpenStack API to provision machines, Puppet to control our servers, Ansible to control desktops, and we're currently also moving to working a bit more with Docker containers, where we make pre-built images and roll out those. So let's take a look at our front end. I would say it's a fairly typical mono front end, so we use Angular 6 and TypeScript and RxJS. So how many of you are Java developers? Okay. How many of you are Java developers but didn't raise your hand? Oh, there are actually people. Okay, no worries. So I think Angular is awesome when you're a Java developer because now with TypeScript you can write properly typed code in the browser. So there's like classes and interfaces and even generics. So I love working with TypeScript. RxJS is awesome for doing asynchronous stuff. So we have Angular for the HTML templates, TypeScript for the business logic, and RxJS for the asynchronous stuff. What are we missing? Something that Java developers typically aren't really good at. Oh, come on, you know it. CSS, yes. So there's this thing called CSS for Java developers, which is Bootstrap. So we've been using Bootstrap extensively to kind of factor away all the nitty-gritty CSS details. Currently, we're also looking into Angular Material, because Material integrates fairly well with the Angular CLI, so it's fairly easy to generate new components using Angular Material. Some responsive design in there to run on multiple devices. I try to make the front end fail gracefully whenever the backend fails. So when one backend service is failing, only the part of the front end that's connected to that part of the backend should fail, and the rest of the system should still be usable. So we also try to test this to make sure that whenever something fails, only a little part of the front end fails, and the rest is still usable. And we had the situation every now and then that we were thinking, oh wow, it's nice and quiet, no errors in our logging system. And then in reality, all the connected browsers were continuously spewing out errors to their console because we made some front-end programming error and we weren't receiving any requests to the backend. So what we've done is reroute all console logs that happen in the browser, so console.log or error, send it to a REST endpoint, which then goes to our centralized logging solution. So we now also know what's going on in all the connected browsers. But beware. This is a nice recipe to perform a denial of service attack on yourself. Whenever something breaks and it starts spamming to the console log, make sure you have some throttling in there. For example, when you have 10,000 repeating messages, it's better to write one message to your log system that says repeated 10,000 times than to write 10,000 log messages to your log system. So every now and then we're building something and it takes a bit longer than one sprint to build it. Or maybe something that we want to test on a separate environment before we release the production. So how do we decouple building something from releasing it and deploying it? So we use feature toggles for this. How many of you have heard of feature toggles before? Okay, about half. So feature toggle is basically like an if statement in your code that is controlled by either a centralized server or a configuration file. So what we typically do is we build something new, we build a feature toggle around it, and then we say, all right, this is enabled on the development environment, it's enabled on the acceptance environment, but not in production, for example. And this allows us to stay away from keeping long-running feature branches, but just merge everything to master, deploy it to production, but not enable this feature yet. So we have a nice backend running with microservices, and we're building a front end. And how do we prevent that we are now integrating everything in front end and creating a monolithic front end? So we didn't. So we built one big front end that was calling all the microservices in the backend, and we're now trying to apply the principle of microservices to our front end too. So splitting it up in different parts, try to find stuff that we can reuse. So we've now created a couple of front-end components that are standalone projects, so you can just check them out and run them. And there's a demo in there, and these components built as libraries, and we can reuse these libraries in our front-end projects. So stuff that we often do, we try to keep those in components, and then reuse those components in the front-end. But the front-end is still the place where we integrate all the different parts. So let's talk about the backend a bit. But first, let's dive into microservices, because I said I was going to talk about microservices. We're in 30 minutes now, and I'm only starting now. So microservice is typically small. It is one thing. Well. It runs in its own process, and therefore you can independently develop it. You can upgrade it. You can scale it. I think microservice should have its own data store. It's typically distributed, otherwise it's not of much use. And it can be polyglot, so you can use multiple languages for different services. We've started doing this by introducing a bit of Kotlin, but most of it is still Java. And they better have some form of lightweight communication, because you're going to communicate a lot. So did we start building microservices right away when we started? No, we didn't. So why did we do? I think there are two reasons. First was scalability. So we both want to scale different parts of our system independently, but also want to scale the amount of teams. If you are working on one repository with 5 teams, chances are that you will hurt each other somewhere, conceptually, not actually hurting each other. Modularity also, so we want to have independent development of different parts and independently deploy them. If you have a system that's consisting of 1 million lines of code and you change one, then it's typically better to deploy only one line or maybe 10 or 100 lines of code than just deploy the entire system. And microservices were becoming cool. We wanted to be cool, so obviously the cool factor helped a bit. So how do we go there? Well, no shocker there. We split our system up. So we try to look to the ideas given by domain-driven design. One of the ideas is a bounded context. So domain-driven design says when your system is large enough, it's impossible to create one unified model for your entire system, because a customer or a client can be different in one part or another part of the system, or an order, for example. So when you work in bounded context, you're saying it's all right to have different models for different parts of the system, as long as you're very clear about the boundaries of those parts and the interactions between those boundaries. So what are the interfaces between different parts of the system? This maps fairly well to a microservice. You can have different implementations within every service, as long as you're clear about the contracts between services. So for each model we defined, where each module was kind of similar to one bounded context, we create a service, and then for every service check, is it now only one part of domain, or are there multiple parts of domain in there? If there's only one part, we're good. If not, we should split it up more. So did we split up everything from the start all the way in small components? Well, that was a bit too much work. So we started out with taking the easy parts, something that's obviously a service that's maybe easy to take the code out. And then there was some code that was a bit entangled, that was hard to split up, so we kept that in one last service. And then over time, whenever we need to change something in that service, we would take out that part, put that part in a new service, and deploy that new service. So it actually took about 2 or 2.5 years until we had finally split it up, the last part of the previous known monolith. And this was something like the logic to send emails when somebody had feedback on the system or something. So something that we didn't touch in 2 years. So let's take a look at our backend. We've recently moved to Spring Boot 2, so we're also using Webflux for the reactive stuff, Java and Kotlin, a little bit of Kotlin, mostly Java and Maven. They are stateless, which is necessary when you want to scale out over multiple services, so we don't store any state in memory in our services. We have one service running in one jar in one JVM, and there's one Git project, so we have lots and lots of Git projects, about 150, I think. And we try to not share too much code between services. We used to do this in the beginning, but it didn't really work because this was creating all kinds of dependencies. So we're only sharing stuff that we need in every service: security, authentication, authorization, and logging and metrics. And for all the other stuff, we rather copy it between services than create a dependency between those. We used to make stuff high available by using load balancers. Now we've moved to using service discovery. I need to warn you a bit about service discovery because I think it's an advanced microservice pattern. Do you need it? Probably not. Do we need it? Well, you know the answer. We think we do, but for reasons. These reasons are we want to have high availability and load balancing without having single points of failure. So if you add a load balancer, then that load balancer becomes single point of failure. You need to add another one, then you have two, and you need to put a load balancer on top. So that's a bit difficult to get right. We want to have secure end-to-end communication between client and server. So if you have client server, you put a load balancer in between, you need to do some sort of SSL termination. We were using Kerberos, and Kerberos is very picky on DNS verification. So the forward and reverse DNS need to match. When you put a load balancer in between, it's a bit difficult. We want to scale out horizontally, which can be done with load balancers, but then you need to dynamically reconfigure the load balancers, which is also a pain. And we want to have some form of automated response to failure. And also being able to move components to, for example, a different data center. And this is also hard when they're between a load balancer, behind a load balancer. I want to do downtime-less deployments, so deployments without any downtime. So what did we do? We did a small selection on service discovery tools that are out there. We looked at a couple ones, and we liked Console the most, mostly because Console had pretty good access control lists about who can use what. So let's say that we have a service called service example, and there were two instances running, so 0 and 1. We have a Console cluster running, so Console is the service registration tool. It's a registry that keeps information on which service is where and if it's healthy. So whenever these services start up, they register themselves to the Console cluster. So Console now knows I have service example. It has an instance of service example 0 and service example 1. So then on our web server, there's a little tool running called Console template, which is a templating mechanism for Console. And this generates a configuration file for our frontend. So it's basically saying service example, column, and then an array, service example 0 dot entire URL, service example 1 dot entire URL. So it knows that if it needs to reach service example, it can go to those two URLs. So then when a user connects to the web server, gets sent back the Angular application, then we set up a stateful connection. So this is a server sent events connection, which is comparable to WebSockets. Server sent events is a browser standard, but unfortunately it's not supported by Internet Explorer and Edge. But luckily for us, we only need to support Firefox and Chrome, so then we can use SSE. It's very nice, but WebSockets will work about as well. So what now happens is whenever a service breaks, for example, instance 0 breaks, Console is continuously checking the health of this service. So if it breaks, Console knows, all right, for service example, now I only have instance 1. And instance 0 is dead. So Console template updates the configuration file here. We push the update to the connected browser. So now this browser also knows if we need to go to service example, I can only go to instance service example 1. So what is the result? Say we have 3,000 connected browsers. We kill a service here. Within 1 second or so, all those browsers know that they shouldn't be sending requests to instance 0 anymore, only to instance 1. So this works fairly well in terms of scaling or restarting services. For the backend, for service-to-service calls, we use the Spring Cloud suite. So there's Spring Cloud Ribbon, which has the same kind of client-side load balancing. So the patterns we use are client-side discovery, because the clients detect where to reach the services, and self-registration. So the services register themselves. Whenever a server starts, it registers itself to the Console cluster. And also, this also helps in finding back your services. So you can see you have an overview of how many instances do we have per service, what are their URLs, are they healthy? So whenever I go to the Console UI, I can immediately see how many instances are running on which environment, are they all healthy or is there something going on? So it also helps a lot in the observability of those types of systems. So how do we develop and test stuff? We develop based on feature branches. So whenever we start working on a feature, we create a new branch with the same name as the fabricator ticket. We start working there, and we don't merge it back to master until it's done. So the master branch should always be releasable. We should be able to deploy the master branch to production at any time. So on our test environment, we run the master branch, and feature branches only run on the local machines and on the CI server. So if we have a system that consists of, I don't know, somewhere between 100 and 150 components, whenever we run this locally, should we fire up, check out 150 Git projects and start those all up? Well, rather not. So we typically only run the components we work on locally. And for the rest, the other services, we connect to the test environment that's already running on OpenStack. So you typically only have 1 or 2, maybe 3 services running locally, and for the rest, you just connect to the running test environment. So testing, I'd say it's fairly normal. Unit tests, mutation tests. How many of you have heard of mutation testing before? Okay, a couple. So with mutation testing, you use a test framework that deliberately makes changes in your production code. For example, changing return true to return false, changing a greater than to a less than, and then run a test suite. So the idea is that for every change you make in your production code, you should have a failing test. If you can change something in your production code without having a failing test, then there's no coverage on that part of your code. So mutation test and mutation coverage tells you a bit more than just code coverage, because it's fairly easy to create 100% code coverage without asserting anything. Been there, done that. Sorry for that. So about integration tests, we use Spring Boot integration, where we can fire up a Spring Boot container inside a Maven integration test phase. We use in-memory data stores, so we fire up embedded Mongo, embedded Kafka, embedded Cassandra, put data in there, and then use rest assured to test REST endpoints. So if a test like this succeeds, we know that Spring Boot container starts up, we can connect to data sources. If we inject this type of data in the database and then do this REST call, then this reply is being sent. So this gives us a fair amount of confidence that the service will also run on our test environment. Protractor for end-to-end tests, because it's the de facto testing tool for end-to-end testing tool for Angular, and Gatling for load tests. How many of you have heard of Gatling before? Okay, well, almost all of you, so no need to explain. What we do is we run Gatling tests on our most important services twice a day, in the morning and the evening, and then we record the average response times, and we store those by a plugin in a Jenkins machine. And there you get this graph, which is deliberately small, so you can't read what's in here. But we have these graphs that give the average response time, well, let's say during a sprint. So whenever there's a peak in this, we probably introduced a performance regression because response times are going up. So during a sprint, we are looking at the response times of our test environment, which obviously isn't representative for production. But the idea is, if the response times in production are okay now, if they are okay now in development, then it should stay about the same. Whenever something changes in development, then we need to look into what changed there, because we might get issues in production too. So how do we test feature branches? So we spin up branches on the CI environment and test it there. And if there are any dependencies, let the test just connect to the test environment. And we try to avoid changing multiple components at once, because then it's difficult to set up the test environment. If you do need to change multiple components at once, we use the YOLO methodology, which is just like push it and hope that nothing breaks, and if it breaks, be quick at fixing it. So try not to be too principled about that. So about building and deploying, we use the open source edition of GitLab for on-premise Git. Jenkins with a couple of Docker Swarm slave nodes so we can scale our builds. Jenkins 2 pipelines. Nexus to store artifacts, Sonar. Well, this is all fairly normal Java development setup. So how do we manage all our builds? I think we have currently about 140 builds. Do we click those all together in the Jenkins UI? Well, I'd rather not. So we try to create reusable build definitions by using the facilities that Jenkins provides us with scripted pipelines. So if you want to learn more about this, I did a talk about it once for the virtual jug. You can look it up online. There's also some of the pipeline scripts that we've created that are on the police GitHub repository, so you can check it out there too. For making reusable build definitions, Jenkins 2 really works for us, because, for example, a Maven build is the same for all our projects. Just do a Maven verify and maybe some instrumentation for code coverage, but it's essentially the same. So we have lots of build definitions that are all calling the same generic build definition for a Maven build. Same for Frontend and some other stuff. So how do you deploy stuff? So what I'm going to tell is per service. So this is the deployment scope of one service. So whenever you push something to a master branch, it is a release. So it's a Maven release. It gets stored with a version number in Nexus. Configuration is embedded in the jars. So we have property sets for test, for acceptance, and for production in the jar, which means that we can use the same binary. When we create a binary of a jar once, this binary travels from test to acceptance to production. And then we use -d spring.environment is dev or acceptance or prod to select the right property file. So there are no secrets in those property files. Secrets are provisioned in another way, but just configuration like where to find the database, for example. So we did use Rundeck and Puppet to do deployments. Currently, we've moved to deploying with Nomad. Nomad is a tool from HashiCorp, which is like a scheduling system where you have a couple of nodes running that stuff can get deployed on. We just say tell to Nomad deploy 3 instances of this server to our cluster, and then we're good. So it's comparable to what Kubernetes does, but without containers, I would say. So if you have I think we have about 100 running pieces in production. How do we know what to deploy and where to deploy? We could keep this in Excel sheets, but that probably wouldn't be a nice way. So we try to minimize the administration we do and the think time. It should be easy to just perform deployment. So what do we do? On a test environment, we deploy at every commit. So whenever we commit, it's a release, we deploy. During a sprint, we take everything that's now on the test environment and deploy everything to acceptance. So just for all the services running on test, find out which service is running there, and now deploy that version of that service on acceptance. So we don't need to do any administration, just take everything from test to acceptance. Same thing for production, after the sprint. Push a button, take all the services that are on acceptance, and deploy all those versions on production. So this helps in terms of keeping a coherent set of services, because whenever we test on acceptance, we know that over there we can check that everything works well together. And we can deploy this set to production without having to do too much extra testing in production. But it also gives us the flexibility to deploy one component from test to acceptance to production when necessary. So when there's one service broken, we can just fix this one service and get this through the whole pipeline. So running in production, we use Greylog for logging. Greylog is comparable to the EOK suite, but I found it a bit easier to set up and use. It's a bit less flexible, but it's good enough for us. Also metrics provided by Spring Boot Actuator. We use Zipkin to trace requests over services. Grafana for some graphing. And monitoring using Sensu and Flapjack. And we automatically log stuff like what is the service that this log statement is produced by, what is the environment, and what is the user ID. So this also allows us to trace all logging created by one user to our system, for example. So did we have any challenges? Yes, obviously. So about sharing code, we try to share as little code as possible. So currently we prefer to just copy a bit of code to a different service instead of creating a library that both services now depend on. We split our backend up into services and then recreated the whole thing as a monolithic frontend. So there's also something to keep in mind. Think about modularity and reuse too in the frontend. Don't be afraid to rebuild. Whenever we need to change a service that we've built, I don't know, a year ago, and we open the code base and we don't really understand it, then sometimes it's easier to just throw it away and build it again. It can take less time than to try to understand what the service is doing. If you have a good set of tests, then it's probably easy to throw it away, rebuild it, run the test, and make sure that everything is all right. We're running stateless, so that we need to perform authentication and authorization at every request, and this can be a bit heavy. So whenever we first went live for a considerate amount of users, we need to scale up our LDAP cluster like crazy because we're doing LDAP calls at every request. So we added a little bit of caching there that these user data is cached for maybe a couple of minutes to drastically remove the amount of calls to our authentication server. It's vital to have teams that can do everything they need to do to get from idea to running software in production within that team. If you need to depend or wait on somebody else outside your team, you're going to be slow. So make sure that the team has the power to do everything they need to put stuff in production. And we have a product owner that's very quick with developing new ideas. And there was a period when the new ideas were flowing in, and as a team we were jumping on the new ideas and working on it. And then after a couple of months, we had 3 products that were almost finished. So now we try to take a step back and first put stuff in production and finish it up, and then start on something new. So stuff we like to work on. Well, actually, we've already done this. So create cross-functional product teams that are responsible for building and maintaining one product. Automate security testing. If you have any ideas on open source tools to do automated security testing, please visit me after the session, because we don't have that much. Our dashboards can be a bit better. Our alerting must become better, something we're still working on. Nomad currently helps us to do zero downtime deployments, so that's something that we're progressing in, and we're still working on making the front end a bit more modular. So I'm currently 10 seconds over time, so there is room for questions, but not during the session, but afterwards. So if you have any questions, feel free to come towards me and ask your questions. I'll publish the slides on Twitter. If you have any questions, also feel free to connect to me on Twitter. I would like to thank you for your time.